Okay, thanks everyone for staying, and thanks for the invitation to give this talk. So I'll be discussing how to get circular lower bounds from learning algorithms, and this is part of a broader context in theory of computation, where we're trying to build like new bridges and connections between two areas, algorithms, where we want to achieve upper bounds, and complexity theory, where we are interested in impossibility theorems. And results connecting these two areas, they have been extremely successful over the last maybe 10 years or so. So here are two examples that go in both directions. So the first one is Ryan's lower bound against ACC0 that was obtained by designing a new SAT algorithm. So this is a connection that goes from like you get better algorithms, you can get lower bounds. And we also have the well-known CIKK result, where they get a learning algorithm for AC0 parity using insights from circuit complexity, like natural properties. Okay, so in this talk, the focus is going to be on obtaining complexity lower bounds from learning. And there's an interesting feature of this setting, which is that in a more recent result, we are also able to connect the design of quantum algorithms with circular lower bounds. So that's something we can get in the learning setting right now. All right, so yeah, so let me start by giving some background in Boolean circuits and learning. So for this audience, I don't need to say anything about circuits. Let me just say that, yeah, we have been stuck. I guess most people still believe NP is not NP/poly, but it is consistent with our current knowledge that all these different exponential time classes, like non-deterministic, randomized, and also quantum, you can simulate these uniform algorithms using like non-uniform classical devices of polynomial size. Okay, so we don't understand non-uniformity. They can do maybe they can do a lot of things. Will be very unexpected. For the purpose of this talk, it's good to have some fixed circuit class in mind. So my running example will be like threshold circuits. So remember, a threshold gate is just a weighted sum, and you check it against a threshold. If you have just a single threshold gate, it's quite easy to understand what these things cannot do. But once we stack together two layers of polynomially many threshold gates, then these things, they start to decide like interesting subsets of the hypercube. And here again, as far as we know, just two layers with polynomially many threshold gates, they might be able to simulate exponential time algorithms. Okay, so understanding the two threshold circuits is a frontier. So when I talk about like a circuit class, maybe you can think about such circuits. Okay, now learning. So we're going to be using the standard model of learning under the uniform distribution with membership queries. So here we fix a class C of Boolean functions, and your learning algorithm has now membership query access to some unknown but fixed function from C. So your algorithm can make queries to f on some points and get the corresponding value f of x. So for instance, maybe your f is some unknown depth-2 threshold circuit of small size. You're querying this circuit, and your goal is to produce a hypothesis h that approximates this unknown function f, okay, such that the error under the uniform distribution is at most epsilon. And in this talk, I'll be considering learning algorithms that can output any hypothesis, so your circuit doesn't need to be a depth-2 threshold circuit. Okay, so that's learning with membership queries under the uniform distribution. And you can consider extensions of the model. So if your learning algorithm is randomized, now the learner can use its internal randomness to make decisions about which points to query, for instance. And now what we ask is that with high probability over the randomness of the learning algorithm, a good hypothesis H is obtained. Okay, so just randomized learning with membership queries. And I want to stress that for the results discussed in this talk, the stronger the model, the better the result. Okay, so we're going to be extracting circular lower bounds from learning algorithms. So if I give you more power, I allow you to do membership queries. I only require you to learn under the uniform distribution. I'm making your life easier, so it might be easier for you to design these learning algorithms, and we're going to be getting lower bounds from them. So this will also give you lower bounds from a packed learning algorithm. So if you can come up with a packed learning algorithm, then in particular I can get from it a learner of this form, and I can extract the lower bounds. Okay, so the stronger the model, the better the result. And yeah, we have some very interesting learning algorithm for different classes, like DNFs, AC0, AC0 parity. We can do in quasi-polynomial time. But for some classes that are also potentially very weak, we have been stuck. So for instance, we can learn a single threshold gate in polynomial time. But again, if we ask the question about depth-2 threshold circuits, can we learn them even in like just slightly less than 2 to the n time? Then we don't have this algorithm. We don't know if it exists. So it's an example of a class where, if you look at depth-1 circuits, we have lower bounds, we have learning. You move now to depth-2 threshold circuits. We have no lower bound, we have no learning algorithm here. And this hints at that there might be like deep connections between, getting learning algorithms for a class and proving lower bounds against the class. Okay, so we are stuck. We can even design an algorithm that runs in time slightly less than 2 to the n. So a natural question is, can we use quantum algorithms? And can they help us getting better learning? So for the talk, we are going to consider the standard extension of this learning model. So now we have quantum query access to this unknown function. So this is the standard query access model in quantum computing. And your goal here is similar. So now with high probability over the output of this quantum learning algorithm, you want to generate a good hypothesis. So just to make this a little bit more concrete, if you're not familiar with quantum computing or quantum learning. So in the classical setting of learning, you can think of your learning algorithm as just a uniform sequence of oracle circuits. So these oracle circuits, they correspond to your learning algorithm, and the oracle is the function you're trying to learn. So here, you're going to have a uniform sequence of quantum circuits, and again, they have an oracle, and it computes according to this unknown function. Okay, so that's the model. And at least in principle, quantum learners, they might be significantly more powerful than deterministic and randomized learners. So we know quantum algorithms can do many surprising things like computing factoring in polynomial time, solving hard optimization problems in much better than 2 to the n time. So perhaps quantum learning algorithms can help us learning expressive classes, at least in time slightly better than 2 to the n. So here the question is, can we achieve such quantum learning speedups? Okay? And going back to this class of depth-2 threshold circuits, can we learn, quantumly learn such circuits in time, say, 2 to the 0.99 n? And again, we don't have an answer to this question. So now I would like to get back to these connections between learning and lower bounds. And yeah, please.
Do we know how to learn polytope, like the end of threshold?
Yeah, that's a good question. So it depends on things like packed model or uniform distribution, weights, your running time. So it gets complicated, so let me not get into this. All right, so I'm going to be discussing computational hardness from learning. And I just want to point out that this paper of Furnau and Clivens from about 15 years ago, that's where they established the first formal connections between getting learning algorithms and improving lower bounds using the learning algorithm. And there's a rich literature on these connections, like how you get hardness from learning. But I won't have time to cover these papers. So yeah, I want to go through some results where improve this original paper of Furnau and Clivens. And I want to emphasize that what they did there is they get lower bounds from efficient learning algorithms. But many interesting learning algorithms that we have, they're not efficient. So that motivates trying to get better connections. So can we also extract hardness from algorithms that run in much larger than poly time, okay? And I have been working on this for many years. So, so these are some of the results I have established with my collaborators. So in the context of deterministic learning algorithms, So in joint work with Adam Clives and Pravesh Kothari, we show that given any circuit class of poly-size circuits, so if you can deterministically learn circuits in this class in slightly less than 2 to the n time, then you can get a hard functioning E, deterministic exponential time, that can be computed by such circuits. Okay, so that establishes a connection in the deterministic setting. So you beat like brute force. Like you can always learn any class by just squaring out the points. So that would take you like 2 to the n time. So this theorem is saying if you could do better than that, then you get a lower bound.
Do you have equivalence queries as well, or not just queries?
Yeah, you can also handle equivalence queries, but for this talk, let's focus on membership. Okay, so this is for deterministic learners. And then enjoyed work with Rahul a few years back. We obtained a connection that now extends the result to randomized learning algorithms. And here it's a slightly more precise formulation. So if you can learn your class with error that is, say, slightly less than half, which is like the trivial error, and your running time is like slightly less than 2 to the n, now you get a lower bound against C again, but your hard function is going to be in BPE, in randomized exponential time. So that's quite natural. So you now have a randomized learner, so you're going to use it somehow to get the hard function, and your hard function is going to be in BPE this time. Okay, and there's a trade-off between your error and the running time here, but just maybe think of the error as a small constant. So this gamma, it's going to disappear. Okay, and more recently, last year, work with Srinivasa Arunachalam, Alex Grillo, Tom Gur, and Arti Sundaram, we obtain a connection in the quantum setting. So the statement is analogous to the previous statement for randomized learning, but now we can also handle quantum algorithms. And your hard function this time is going to be in BQE, in quantum exponential time. Okay, so we have now some quite tight connections between like getting better learning and lower bounds. Just to make it more concrete, so this is just the quantum statement. Again, if we apply it to the class of depth-2 threshold circuits, and say with constant error, then it tells us that if we could learn depth-2 threshold circuits with constant error and in slightly less than 2 to the n time, then we get a new lower bound against depth-2 threshold circuits. Okay, so just a direct application of that result. Yes?
Just asking about BQE, is our state of knowledge about it identical to BPE?
Can you say it?
Our state of knowledge about lower bounds in BQE.
Yes.
Is it essentially the same as BPE, or do you know something?
Yeah,
different?
I'm not aware of better lower bounds that you can get if you go to BQ. Okay, so how can we interpret these results? So there are two ways of thinking about them. So the first is maybe the optimistic approach, which is that now we have a new path to lower bounds. We can explore the power of quantum algorithms, and maybe we can get some new circular lower bounds. But there's also the pessimistic view, which is that we have managed to come up with better quantum algorithms for many hard tasks, but when we go to learning, we cannot get any quantum learning speed up yet. And maybe a reason is, circular bounds are so hard to prove, and if you could get these learning speed ups, you will get new circular bounds. Yes.
Sorry. So wait, in the quantum setting though, we can do Fourier sampling, so
Yeah.
we can learn like with samples instead of queries sometimes.
Yeah.
So what you're saying essentially is we would know how to benefit from a quantum speed up, which we don't have.
Mm-hmm.
We do have a better model in the quantum setting, right? Like we have sampling instead of membership queries for certain classes.
Mm-hmm.
We don't know how to take advantage of that and turn that into better lower bounds.
Yeah, so for instance, you mentioned Fourier sampling. So Fourier sampling actually shows that this connection is tight with respect to advantage gamma. Because Fourier sampling is going to give you like gamma 2 to the minus n over 2. And again, then you could go to like polynomial quantum regime. If you could just barely beat Fourier sampling in the correlation that you get, then this theorem would also give you lower bounds. Yeah, so the theorem works also like in this polytime regime with respect to just getting like some very non-trivial, just barely non-trivial correlation. Yeah, thanks. All right, so I want to go through the techniques, just give you a high-level overview of these techniques. So as we give more power to the learning algorithm, extracting hard functions from the algorithm becomes a more delicate task. And like different papers, they have used different approaches. But now we have like pretty, at least conceptually, they are pretty elementary proofs using the right building blocks. And I'll briefly go through like how to do it for deterministic learners, and just catch the argument that works in the case of both randomized and quantum learners. So there's like a single high-level argument that works in both cases. So for deterministic learners, so now you have your fixed circuit class C, and you have a learning algorithm for C that runs in less than 2 to the n time with low error. So the construction of the hard function here is quite simple. So you're going to run this learning algorithm and simulate the oracle, the function you're trying to learn, as being the zero function, the constant zero function. Okay, so every time this learner asks a query, you just say 0. So you're simulating it over the zero function. And you collect the set of queries made by this learner. So let Q sub n be the set of inputs queried by the algorithm. And I'll do the following. Take the complement of the set. So here's a picture. So Q sub n is the set of queries, and L of n is the complement of the set. And this is going to be your hard function. Okay, so that's the construction. So we need to check two things. First, this is a function in E, in deterministic exponential time. But of course, you're just running the learner. It runs in time less than 2 to the n, and you're just collecting the queries. So you can decide this language in 2 to the n time. And now you need to argue that this function is not in the class. So I won't have time to give you the proof. So it's like a simple argument. But the intuition is that you're running your learning over the zero function, and you're getting this set of queries. So this should work as a hitting set for the class. Because if there's like a dense function in the class that you can't hit with the set of queries, you won't be able to distinguish the dense function from the constant zero function. So this collection works as a hitting set, and this hitting set has non-trivial size because your running time is less than 2 to the n. So the number of points in this hitting set is going to be less than 2 to the n. And that's the idea. Once you have a hitting set, you can get lower bounds against the class, and that's what this proof is implementing here. Okay, so you get a lower bound by just looking at this set of queries in the case of deterministic learning algorithms. So unfortunately, for randomizing quantum learners, this approach cannot work. Because, say, many randomized learners, the only thing they're going to do is to query the function at random points. You cannot hope to extract a hard function from queries at random points. You could have done that by yourself. So we need a different approach. And maybe the most natural thing that comes to mind is, I know how to get lower bounds from deterministic learners. So maybe I can use PRGs to derandomize my learner, and then just use the previous approach. Okay, so here's just the standard definition of PRGs. And indeed, you can derandomize learning algorithms using PRGs, but you need a PRG against non-uniform circuits. So you don't know which circuit you're trying to learn, so that's sort of the reason why you need strong PRGs. But again, we don't have such PRGs. But what this new paper is going to do is to use the PRG in a different way. So instead of using the pseudorandom strings to derandomize in place of R, we're going to sort of use the pseudorandom strings to generate a function that the algorithm is trying to learn. Okay, so we're going to use it in a different way. And here the intuition is the following. So if I have a random function, I can't expect my learning algorithm to learn the random function. It runs in time less than 2 to the n. Okay? So if I have a strong enough PRG, so if its output looks random, then it will be generating some hard functions that are not in the class. Okay, so that's the intuition. If the output of the PRG looks like a random function, well, you can't learn, and therefore it can be in the class, because you like learn things in the class. So that's the intuition. Now let's formalize this intuition. So yeah, think of it as like in the quantum setting, but if you're not familiar with it, just think about randomized learners for the rest of the proof. So we have this learning algorithm for the class. Again, it runs in less than 2 to the n time. So the first thing we're going to do is quantum meta complexity. Okay, you have a quantum learner, and I'm going to get a quantum natural property out of this learning algorithm. And so, again, just briefly remind you, so natural property, now you get the entire function as your input. So you get the entire truth table. You want to reject truth tables in the class, but you want to accept a dense set of functions that are not in the class. Okay? And the difference here is that you have a quantum algorithm performing this task. So that's a quantum natural property, okay? And it's an efficient quantum algorithm in the size of the input. So how do you get a quantum natural property from a learning algorithm? Well, this has been done in many papers. So your learning algorithm, you know that if you simulate it on the input truth table, it's going to produce a good hypothesis with high probability. So we can test this. But on the other hand, if you have a random function, you can't really expect your learning algorithm that runs in less than 2 to the n time to produce a succinct, good approximation, like a compact representation of this random function. Okay, so there will be many functions for which it can possibly succeed. These functions can even be approximated by circuits of less than 2 to the n size. So yeah, so that's how you do it. So you get your learner, and from it you get this quantum natural property. Now, let me have a simplifying assumption here for the rest of the proof. Because this quantum natural property, there might be functions near the border of the class that you might accept with probability close to half. Okay? But let's pretend this doesn't happen. That we have just this dense set of functions that are not in the class. We accept these functions, and we reject everything else with high probability. So that's the new picture. So I have this dense set. I call it h of n, so these are the hard functions. It doesn't overlap with the class. And you can decide this set in quantum polynomial time. Now we're going to use the PRG to generate a hard truth table. Okay, so suppose you had this PRG. So this quantum natural property works as an efficient test. So if this PRG is strong enough, we're going to be able to hit some truth table that is a hard function. So suppose we had this G, so suppose it has like very long stretch. So we generate a hard function. Now again we have this issue. So where does this PRG come from? Because we need to fool quantum computations. But something happened here. Now we're only trying to fool this quantum natural property, which is a uniform procedure. So we got it from the learning algorithm, which is also a uniform procedure. So we have simplified the problem, because now we only need to fool a uniform computation. It's quantum, but it's uniform. And that's what allows us to complete the proof. Okay? So we're going to consider two cases. It's a non-constructive win-win argument. And in both cases, we're going to get a hard function in BQE that is not in the class. So the first case is when I have problems in p-space that can be done in sub-exponential quantum time. Okay, so in this case, this is a uniform hardness assumption. And I'm going to tell you how to build a PRG from this. Okay, so from this hardness assumption, you can get a PRG. And that implements this approach. Now, the second case is where p-space can be simulated by quantum algorithms in sub-exponential time. But now here, like p-space is powerful enough so that you can diagonalize against circuit classes, and you can get hard functions in p-space directly. But now we know these hard functions are also in BQE. Okay, so that's the sketch of the proof in the second case. So in both cases, you get a hard function, except that you need to rely on a PRG construction. Okay? So for randomized algorithms, now you could just use an off-the-shelf PRG construction from this hardness assumption. But in the quantum case, you still need to construct this PRG, okay? And that's the most technical part of this paper. We need to go through like the existing ideas that work for randomized algorithms and make sure they work for quantum algorithms as well, okay? And this turns out to be a bit delicate, but it can be done. So let me just, maybe skip this. All right, so how much time do we still have? I think I started a bit late.
Yeah, five minutes.
Okay, yeah, thanks. All right, so now we have these connections between like learning and lower bounds. And the natural thing to do is, okay, give me a new lower bound using these connections. Okay, maybe design a new learning algorithm, get collect this price. Unfortunately, I still don't know how to do it in a direct way. Like, here's a new learner for an interesting class, and here's a new lower bound. But it's possible to use the connection in an indirect way to get lower bounds. So let me explain how this is done. Okay, so we're going to explore the learning to lower bound connection in an indirect way, and it's going to be a win-win argument. So let's fix the class C to be the class of polynomial size circuits. These are like general circuits. And we will consider two cases. Are general circuits non-trivially learnable in the randomized sense? Can I learn classical circuits? And if that is possible, then we already have a lower bound using the connection, right? So BPE is not in size Pauli. And let's make the following assumption. So suppose I had a problem pi that is complete for BPE, okay? So this is an assumption. Suppose I had a problem that is complete for BPE. Then in this case, I also get that this problem pi is not in size Pauli by completeness. And of course, size Pauli is more powerful than BPP. I get that the problem is not in BPP. Okay, so under that assumption, I get a lower bound for pi that it's not in BPP. Now let's consider the second case when we don't have a learning algorithm. Okay, so learning is hard. Now here's a second assumption. Suppose for the same problem, if I could solve this problem in BPP, then this implies that learning is easy. Okay, suppose I had this implication. Because I'm in the case where learning is hard, it follows that the problem, again, is not in BPP. Okay? So if I could establish the two green boxes, then I get unconditionally that for this problem pi, it's not in BPP. I need completeness for BPE under non-uniform reduction. And I need that this problem is connected to learning. So if it's easy, then learning is easy. And it turns out that there is a natural problem with these two properties. And it's a problem in time-bounded Kolmogorov complexity. Okay? So yeah, you already know what is KT complexity. You know it's a long-standing problem to show that estimating KT is not in P. You have also seen by now the randomized version of KT. And that's the problem, like estimating RKT complexity, whether your input string is a structure, it has complexity at most n to the epsilon, or it looks like a random string. Unconditionally, this cannot be done in randomized quasi-polynomial time. So that's a proof that uses the learning connection.
But it's not quite complete, right?
Yeah, it's that's the sketch of the proof. All right, so yeah, I'm almost done. So let me just make a comment about deterministic versus randomized versus quantum. We know it's like this is an open question, right? So MKTP is not in P. So when in this deterministic world, this looks hard to solve. Once we move to the realm of randomized computations, we have an unconditional lower bound. We know that for MRKTP, this problem is not in BPP. So the message is that once you increase the computational power, you move to this more powerful model. We get more algorithms. So it's easier for us to do things like diagonalization and like indirect diagonalization. We know more randomized algorithms than like deterministic algorithms. And that's like the main idea here. And the reason this proof doesn't work for the deterministic case is, again, there's a kind of implication that we can do with randomness. We don't know how to do it deterministically, okay? And the moral is that now we have these connections in the quantum setting. Are there quantum algorithms that we can use to get new unconditional lower bounds? Maybe exploring this quantum computations in an indirect way. Yeah, and I would like to finish with a concrete open problem. And this has to do with the direct approach to lower bounds. So we can, I show how to get them in an indirect way. But now, can we just plug in this connection and get a new lower bound? So this is the question. So it's not hard to design a natural property against match end circuits with bounded bottom funny. Okay, there are different ways of designing this natural property. One is by this class is learnable, so you can get a natural property for it. Now my question is the following: can we have a natural property against the following minor extension of this class? Is an OR gate of match ends. This is like quasi-polynomial size circuits. And for this OR gate at the top, I assume it's a disjoint OR. So this is a circuit where whenever this top gate evaluates to 1, there is exactly one input wire that evaluates to 1. Okay, it's a semantic constraint. So my question is there a natural property or even a quantum natural property against DOR merge end circuit of quasi-polynomial size? And we can do it for merge end, so it's just one layer and a DOR gate at the top. And if you could do this, then we would separate quantum exponential time from ACC0. Okay, so thank you.